but I think you can find this book very easily. Okay, so this might not be a problem finding this book. Okay, maybe some of you maybe having a copy of this book in the class. Does someone have a copy of the Gellert book? No. Okay. Okay, try to find this book. Okay, if you have a problem coming to the library, because the library is open. Okay, so you can take a copy from the library. Okay, or otherwise, if you are not successful or you are not able to come to the university, or somehow you couldn't find it, you can ask me, and then I can share the screenshots of the problems or the examples. Okay, is that okay with all of you?
Yes, sir, that is better.
Okay. Okay, now everybody can see the screen of my computer. Is it visible to all of you?
Yes,
Yes,
sir.
sir, it is visible.
Okay, Bismillah ar-Rahman ar-Rahim. Okay, now this is week 10. Okay, welcome to week 10 in steel structures. Okay, now in this class we will start discussing the flexure members, which we call beams and girders. Okay, now as I told you that these lecture slides we have been modifying this lecture slides. Okay, and my colleague Dr. Muhammad Fahad and I have been working on the slides. Okay, the slides is what I'm teaching. They are jointly developed by myself and Dr. Muhammad Fahad. Okay, so the title is the banding members, or you can just slash, you can note it with you that it means the beams and the girders. Okay, so what we are going to discuss in the beams and girders are listed in this slide. Okay, so first we will have an introduction, what we call a bending member or beam or girder. Okay, then we will discuss the plastic moment and the bending stresses in the beams. Then we will discuss the stability. Okay, stability issues with the beams. Okay, as I told you, in the steel structures, stability is an issue. Okay, then we have also seen that in the case of tension members and the compression members, there is a slenderness ratio. Okay, that is about the stability of the member. Okay, similarly in the beam case, we also have a stability problem. Okay, so how you should know about the stability problem, or you should be aware about that, what are the different mitigation measures you have to take to enhance the stability of the Ariza beams. Okay, now we will have a discussion on the classification of the shapes, basically like what are the different shapes we are going to use as beam or girders. Then we will have some how we can calculate the bending strength of the compact section. So we will also have a discussion on the shapes or sections, that what are there are three kind of sections. We call them compact sections, we call and non-compact section and cylinder sections. So up to here we will cover all these topics in this class, and in the next class we are going to cover the remaining topics. But one thing you should remember, that when we are talking about beams, and from your knowledge of your previous courses, so we know that in beams there are two type of reactions or actions which are generated. Okay, what are those? They are flexure. There is a flexure and there is a shear. Okay, and then we have a stability issue in the beam. Okay, so we will discuss flexure in this class. We are not going to discuss shear in this class, but in the coming slide classes we will discuss shear in the beam. Okay, but in this class we are going to discuss the flexure and the stability. Okay, so this is the agenda for today's class. Okay, now we will start with the simple introduction, that what we call beams. Okay, beams are the horizontal members which are subjected to transverse loading. Okay, and they do not have these axial forces. Okay, which are acting on the member. Okay, so beams are the structural members that support the transverse loading. Okay, and what are the actions that are generated But in the beams, we know that there is flexure or bending and there is shear. Okay, as we are interested, or we will discuss the flexure initially. So that's why the shear is not being mentioned here in this statement. Okay, but there is shear that is also generated in the beams, okay, as a result of these load acting on the member. Okay, so the important another highlight of this slide is the differentiation between the beam and the beam column, as we discussed in the last class when we were discussing the compression member, that if you have these axial forces acting on the member, then this member we call beam column. Okay, this is not called a beam only. Okay, once you have these forces, axial forces, which are acting along the longitudinal direction of the member, then this is becomes a beam column. And if you go to your specification, and that specification is AISC, and in AISC there is a different design and analysis approach for beam column. Okay, and there is a different design or different recommendation for beams. Okay, so important thing is that you should note it down with yourself that there are difference between the beam and the beam column. Okay, and some actions that are generated in the beams are the flexure and the shear, but flexure is more of our concern from the point of view of today's lecture. Okay, so if we want to look at the beam column, and we want you have another example. So a compression member, when it is subjected only to axial loading, but at the same time it is subjected to any lateral loading such as wind load or earthquake load. Now this is not a column, so it is, we call them beam column. Okay, I hope this is clear to you. Okay, so this is like that, just to differentiate how we can differentiate between beam and column. Okay, so beam on the horizontal members. Okay, and they are subjected to this transverse loading. So the different cross-sectional shapes. So as we discussed that we have this specification, and our specification we call it AISC manual, and AISC manuals there you can find in the chapter number 1 about the properties of some of the geometrical shapes. And these geometrical cross-sectional shapes we call hot rolled sections. Okay, so they are hot rolled sections. So AISC applicable to the hot rolled sections. Okay, now for beams you can use the hot rolled sections. Okay, what are the most commonly used cross sections for as a beam? So we can use wide flange section, we can use the standard American beam, we can use miscellaneous cross section. Okay, so these are the some of the cross sections or the shapes or hot roll shapes you can use as a beam or as a column, or just sorry for my statement, as a beam or as a girder. Okay, so important thing is that what is the difference between a wide flange section and an American I section, we call the S section. So just before the class I was just looking about the information that how we can differentiate. So there is a difference. Okay, now the flanges in the I shape or S shape is they are tapered, but in the wide flange section the flanges are not tapered. Okay, and the flanges and the web are approximately of the same thickness in case of the wide flange section, but in case of the standard S section or standard I beam section or American I shape section, sorry, the web and the flanges are of different thicknesses. Okay, so apart from these shapes, the wide flange shapes, so channels can also be used as beams. Okay, now, and apart from these hot roll sections, we can also use the built up sections. Okay, now the built up sections, why we need to use the built up sections? When the demand on your member is very high and you cannot find appropriate section. Okay, the first thing is that you should remember that the cross-sectional area is very important. Okay, what we have discussed so far in our previous classes, that we have to increase the cross-sectional area, whether it is gross area or is it effective area or it is net area. So once one member is not enough, what we do that we combine the two members like this. So for example, we want to use an angle. If one angle is not enough, so what we do, we come up with the double angle. Okay, so we can come up with a double channel as well. Okay, so if this is not enough, we can come up with the built up section. And for example, in Pakistan, you do not have these hot roll sections which are available in the market, or not all of the hot roll sections are available. So what you can do, you have these plates. So what you can do, plates, you can combine them together to build a section. So this type of section we call the built up section. Okay. So this is I built up section, or you can use a box built up section. Okay. So these are some of the cross sections, example of the cross sections you have to use, but most importantly, most of the time you will be seeing this white faint section, which will be used in the examples. Okay. Now, another thing we have to see that what are the most efficient section for beam or the girder. So you will be seeing, oh, in the statement, or this slide is demonstrating that are doubly symmetrical sections, okay, doubly symmetrical section. And you guys are familiar what is meant by the doubly symmetrical section. For example, this is an I section, okay, and the flanges are of the same width, okay, and the web is of the constant, it's a prismatic section. So I'm sorry for my drawing. So there are two axes, and about the two axes the cross-sectional or shape is similar, or there is a about x-axis. For example, this is a mirror image of this one, or this is a mirror image of this one. So such sections we call doubly symmetric sections. Sections are very much efficient. Okay. Okay. So okay, I talked about that ASI, that we use the hot roll sections. For example, you are familiar, you can, according to the situation or the scenario, the hot roll sections are perfectly working with you, or it serves your purpose. So what you can do, you can simply use these ASI guidelines. But where to find these guidelines or recommendation about the beams in the AISC manual? So you can find in chapter number F4, chapter number F. In chapter number F, you will find the design members for flexure. So specification or recommendation of the AISC. Okay, this is a recommendation of AISC, okay, when you are dealing with the bending only. So you can find it in the chapter number F. Okay, so if you are dealing with the shear as well, okay, you can find the appropriate recommendation of AISC in the chapter number G. So there are two chapters, okay, chapter number 1 and chapter number 2. Okay, Ahmad, if you want to get going with the steel structure, so another important thing you should note it down is that you have to familiarize yourself with this manual. Okay, without this manual you cannot do the design. Okay, because it has a lot of design aids in the manual. Okay, so you have to consult them. Okay, so once
All right.
you want to get going with the steel structure, so this is very important. If you really want to learn it, so you should go to your manual and you should open and try to find chapter number F and chapter number G. Okay, this is a home assignment or home activity. Okay,
Okay, sir.
honestly, yes, please. You are saying something?
No, no, sir. Just I said all right.
Okay, actually, honestly, I haven't opened the manual, and I haven't I haven't opened the manual to find these chapters. Okay, but you can do it. Okay. Okay. So there is a problem with the slide. Okay, this is loading. Okay, I will go back. The first point is that you should note it down. This manual is very important. Very important for design. Okay, you can say design of steel structural member. Okay, I'm sorry for my poor writing. Okay, this is very important. Okay, you have to be well versed with this manual. Okay, so as I told you that there can be two type of sections. Okay, based on the availability in the market. Like if you have hot roll section, you are doing some analysis or design in the America or some another well-developed state. So what you can do, what you can get is that hot roll sections are available. So you do not need these sections, okay? So there are two type of sections which are commonly used for as beams or girders. We call them hot roll doubly symmetric I shape, or forget about the other description. So you just remember hot roll sections and built up sections, okay? Built up sections. I have missed a L here, built up sections. So once you are doing the analysis and design, and if you want to select the cross section for your beam, so there will be two possibilities. You have so you can weld them together or you can bolt them together to get a cross section, okay? So these are the two choices you have in case of beams, okay? In case of beams or any other member you want to design or analyze, or if you don't have the required cross section, you can go with the built up section, okay? Is that okay with you? So okay, now what are the different types of built up sections, okay? Like for example, you have a beam, okay, like this, and the bending moment is like this, okay? So if there is a bending moment like this over here, the bending moment is maximum. Over here, it is the magnitude of the bending moment is reducing. Okay, it is very less if you go towards the support. Okay, if you draw this a simply supported beam, okay, and you just have a point load. So what you can do that for here, you can use this where the bending moment demand is very high. You can come up with the built up section. You can just add plates to the wide flange section or the hot roll section, okay, in order to increase the capacity of the member, okay. Or you are going towards this one, you can use a taper section, okay. With the taper section, like over here, the cross-sectional dimension will be higher, but once you are going from the mid to the support, so the beam will be tapered section, okay. Now these are some of the things what you have to do, or you might see in the field that what you do, you use cover plated beam, okay. What you do, you attach plates to the flange, okay, where the moment is large, okay. So what other you have to do, you can go with the tapered beam as well, okay. This can reduce the depth where the moment is small, okay. So these are the two important things. So I hope this you will remember, okay. So what you do, what else, you cut the web of the white flange and weld them together. So these are just an example of built up beams. So what are the different various ways how you can save money once you are doing the steel structure design, or if you want to pay more attention to the economy, so then you have to do these things, okay, in the field. So what we see in this slide is the differentiation between the beam and the girders, okay. The members which are connecting columns, we call them girders, okay. The number one, like the figures or the elements in this plane which are designated as 1, okay, 1 and 2. So the members which are connecting columns, we call them girders, okay. The girders. These are the girders, okay. So these we call girders, okay, because the demand is very high on these members, okay. And these we call the beams, okay, or you can call these primary beams, you can call them secondary beams, okay. Okay, beam girders are horizontal members supporting slabs, okay. You are familiar with that. On top of these beam or girders, you have these slabs, okay. So girders span between columns, beams span between the girders, okay. Between the girders, you have beams, okay, and between the columns, the horizontal members we call girders, okay. This we call beam. This is just in different how we can differentiate between a girder and a beam, okay. So what are the different typical spacing which can be used for girders and beams? So These are the beams, okay? These are the beams because they are supported on the girders, okay? So they can be spaced around 3 to 4 meter, okay? Like this is the beam spacing, okay? Okay. So you can see, okay, the girders like they span from some 6 to 9 meter or 6 to 12 meter, okay? So this is just a example of typical spacing, okay? Typical spacing. Typical spacing of beams, girders, okay? Now, girders can be, there are two type of girders, okay? Please remember that first one we call shear connected girders or shear connected beams. Or I will stick to the term the girder, okay? Shear connected girder, okay? What are shear connected girders? Like this is a column, okay? Over here, this is an example of shear connected girder, okay? Like the girder which only transfers the shear from the girder to the column is called a shear connected girder, okay? Now you can see that this connection configuration is enough to understand that this beam can only transmit the shear force from the girder to this column, okay? So this is an example of shear connected girder. So one, if you have some sort of connections which are at the top and a bottom, so we call these type of girders, or these type of girders can also be classified as moment connected girders, okay? Moment connected girders, okay? So these are the two classification of the girders based on the connections between the compression member of the column and the beam, okay? So you can see this is an example of moment connected girder, because a moment connected girder, you have this type of couple we get, okay? So it can just transfer the bending moment. Cannot transfer the shear, okay? Over here, you can see that this can only transfer the shear, okay? It cannot transfer this bending moment, okay? So their girder can be either moment connected or shear connected, okay? So so the girders, like you might be, we have a topic in this course about the composite section. So this is an example of a composite section, okay? Composite section means that this girder is made of a different material and this slab is made of a different material, okay? Like this is a RCC slab, okay? Let me do my poor drawing here, RCC, and this is your steel, okay? And this section as a whole we call composite section, okay? Composite, I hope composite section, okay? Now in this composite section, this is a different material and this is a different material. How the forces will be transferred from the this slab to this beam. For this purpose, what we can do that we can just embed this flange into this slab, or we can provide some sort of studs which are known as, and these studs are primarily meant to, they just transfer the shear from this from this material to this material, okay? And the shear direction is this one, okay? So these type of members or these type of elements we call shear connectors, okay? For example, these are the example of shear connectors, okay? So they can transfer with, if you provide shear connected, some of the forces, or we have to see some experimental work, how much forces are transferred from this member to this member, okay? If we use different type of shear connectors. So for the sake of this class, or for your information, this thing we call shear connectors, and they are connected to slab through shear studs, okay? No, sorry. They are also known as shear studs as well, okay? And they are responsible for the composite action, okay? In this composite section, okay? Is it clear to all of you what I'm trying to discuss? आप लोगों को समझ आ रहा है?
Sir, excuse me.
जी,
This share one and the previous one which you explained on the previous slide, they're quite similar, the moment and the share.
where?
Here the bolts are horizontal, but the second one they are vertical.
So this slide we discussed that there are two types. Girders can be either shear connected or they can be moment connected. Okay.
Yes, you said in the share connected girder, so the bolts are vertical.
Balls.
Horizontal. Here the drawing, the second drawing,
This one.
yes, this one.
Yes.
And the second one that in the second slide they're totally different.
Now this
The
is
second one.
yeah, this is between steel structure members. Okay, this is not a
Okay.
composite section. Okay, so these two members you can join with the connection, which are bolted connection. Okay, over here, this is not bolts. This is a composite section now. And you can provide a shear studs here in order to transfer the forces from this member to this member. If you do it like this, okay, this is a slab and you just place your beam here. So the forces can transfer to this beam through the friction between these two surfaces. Okay, like this, if you do not provide any mechanism from transferring the force from this member to this member, so the only thing left is the friction between this member and this member, frictional force. So once that frictional force is exceeded, so what will happen? This will slide away. This will try to slide.
Okay, sir, that's clear.
Okay.
I got it.
Try to slide. But if you provide some studs, okay, so more forces will be transferred from this member to this member, and this member is a composite section. Okay, so important thing that these things, whenever you see these things, so these are known as shear studs. Okay, they are used in composite section, or they can be used in RCC or reinforced concrete. For example, you want to connect your foundation footing. Okay, like you did some footing. Okay, this is the pad of this footing, and you realize that the depth of this footing is not appropriate. It cannot resist the demand. What you do, you want to do more concreting on that. Okay, you want to enhance it, but the connection is not there. What you are going to do, you will insert some studs, and in this way these two concretes or the concrete passes will become, or they can become a single, or up to some extent you can say a single section. Okay, shear studs or studs you can say. So you might find there are some openings in the girders. Okay, now these openings are meant for services. Okay, services like cables, for example, cables. For economy, or you can say saving in the steel. Okay, now this is the web. Okay, in the web you will find openings, and these openings are meant for the services. Okay, and maybe you want to save some concrete, or sorry, steel as well, so these are there. Okay, you can find these in the industrial units. Okay, okay, now as I told you that in this class we are going to discuss the flexure only. Okay, now the bending action in the horizontal members, and we know that there are two approaches. Okay, there are two design philosophies we have discussed in the class number 1, that we have LRFD, which is known as load resistance factor design. Okay, now according to this philosophy, the applied moment, okay, the demand should be at least equal or less than. Okay, it should be at least equal or less than your capacity. Okay, so this is mu is the required moment strength. Okay, or the demand, you can, for in simple words you can say this is the demand, on the member, and this is the capacity, okay? And there is a strength reduction factor for beams. This is also 0.9, okay? And you will see a subscript here. So denoting that this reduction of phi is meant for beams, okay? So what is AISC, okay? Now AISC, as we discussed in our first class, that this is the loading code, okay? Loading code. Okay, the coefficients of loads we used in different load combination is suggested by this AISC, and this is also adopted by International Building Code. Okay, based on these recommendations, like this code recommends that once if you have a dead load so and a live load together, so you have to use this load combination. Okay, if you just have a dead load, you just consider the dead load with this coefficient. So this is suggested by this AISC, okay? If you have some loads which are acting on your members, and then you multiply it with this load coefficients, and then you can come up with this MU value, okay? Now, phi B is the resistance factor for bending, okay? And Mn is the nominal moment strength, okay? Mu is the demand or the required moment strength, and Mn is the nominal moment strength. Okay, so these you are familiar with. Okay, so the left hand side or the right hand side is the design strength, okay, design moment, and this is the applied strength, or vice versa. Okay, now as I told you that we will use two approaches, LRFT, or we use LRFT and ASD. In ASD you use factor of safety, and this factor of safety in case of beam is 1.67. And what is this MA? MA is the required moment strength, okay? The maximum moment corresponding to the controlling load combination, okay? Similar, okay, this is a very typical value like 1.6. We have seen that in case of tension members, or if I remember, in the compression member, we also use this factor of safety, this value, okay? But if we divide this factor of safety by 1.67, so we will be getting this value. Okay. So this equation can be modified if you add this factor of safety. So this equation will be modified as 0.6 Mn. Okay. Now if you divide both sides by this S, okay, what is S? Okay, like Ma is less than or equal to 0.6 Mn. If you divide by S, what is S? S is the elastic section modulus, okay? So this becomes, or this we call that FB. And FB is the maximum computed bending stresses, okay? And this is called allowable bending stresses, okay? So the allowable bending stresses should be greater or at least equal to the bending stresses, okay, which are produced by the loads, okay. Now, now we will discuss the cross sections, okay. Now, once you have a beam here, okay, like let's take an example of a beam, simply supported beam, okay. For example, it is loaded with a load, point load, okay, and the intensity or the magnitude of the load keeps on increasing. It is not fixed, okay, like it is increases from 1 kip to say 10 kip, okay. Okay, once the load is 1 kip, okay, if you see the curvature versus the moment plot or moment curvature plot of this cross section, so it will look like this, okay. Initially there is some elastic range, okay. The relationship, okay, sorry, the relationship between the curvature and moment will be elastic, okay. So moment curvature plots are very important, okay. One thing is that, okay, let me discuss this one, then I will share my experience with you regarding moment curvature plots, okay. Okay, initially when the load is minimum, so the stresses are within the permissible limit. So you can see here, these are the stresses, the bending stresses. and these bending stresses, you can see the linear relationship, so they are elastic. Okay, there is none of the fiber in the cross section they have reached yield. Okay, the strains are less than yield strains. Okay, so one thing to remember is that this is the neutral axis, and above the neutral axis we have compression. Okay, and below the neutral axis we have tension. Neither in the tension zone or neither in the compression region the stresses or strains have reached the yield strain. Okay, so this is evident from this plot as well. Okay, once you keep on increasing the load from 1 to 3 kip, so this member will slide, and this state of the member we call elastic state. Okay, okay, and once you keep on increasing the load on the member, so some of the fiber will reach the yield. Okay, so this is evident from this plot. Okay, outermost fiber of the member have reached yield. Okay, over here. So if you compare this strain to this strain, so if they are, if we assume that they are on the scale, so this is slightly more than this one. Okay, so if you keep this state is known as elastic plastic state. Okay, so this state is somewhere here. Once you cross the yield moment, okay, and you keep on increasing the demand on your beam, so eventually it will reach the full capacity. And what is meant by the full capacity? Fully plastic is the full capacity of this cross section. Okay, if you compare this slide, okay, you see here, and it is also stating that the strain is greater than yield strains, and the relationship between the stresses is not linear. Okay, this is bilinear now, like this. Okay, so these members have reached the yield. Okay, over here. Now, once it reaches the fully plastic state, so what will happen that you will see that the stresses are fully plastic. All the members or all the fibers in the cross sections have reached the fully plastic state, and this state is here. Okay, and the bending moment we call, which is produced, or the maximum capacity of this cross section, we call plastic moment. Okay, and this plastic moment is about, or the yield moment is about 2/3 of these plastic moment. Okay, so once you are doing modeling of some members, okay, like bridges or buildings, so you will not see the collapse of your model in your software. So what you do, you do moment curvature plot. Okay, what is the state of my member? Okay, so this member, when we do the moment curvature plot, we can identify that based on the curvature or based on the moment, that what is the flexural state of my member. Is it in the elastic range or is it in the inelastic range? So moment curvature plots are, sorry, curvature plots are very handy, very important, very useful, you can say, in the non-linear analysis. Okay, okay, just note it down with you. Okay, now this is the same thing like what we have discussed, the bending stresses. Okay, in the horizontal member, for example, you have this simply supported beam. Okay, and there is a point load which is acting on this member. Okay, so there are different states of this member. First is denoted by state A, state B, state C, and state D. And with these beams you also see the cross sections. Okay, now this is a wide flange section. Okay, this is not an I section or S section. Okay, so the stress or the strain, sorry, the stress distribution is also shown. Okay, okay, with what is state A. Okay, what in state A the member is elastic, in state B the member is still elastic, and in state C your member is partially, this is elastoplastic state. Okay, so you can recognize it from this plot as well. Okay, and this is the fully plastic state. Okay, once you reach this state, so what will happen that thing, or a very important terminology we use, plastic hinge. Okay, the plastic hinge. Plastic hinge will be formed here. Okay, so there is a plastic hinge that is formed. Okay, once you keep on increasing, so there might be some second plastic hinges where that will be formed in the member, and eventually this, once these plastic hinges have formed, so what will happen that this will make a mechanism for the collapse. Okay, like once you have these plastic hinges, these plastic hinges, this plastic hinges, technically saying the bending moment is here, the plastic hinges cannot form here as well. Okay, so just for the sake of completeness, or for the sake of communicating that once when the section become fully plastic, plastic hinges are found at different ranges, in different regions of the member, and these plastic hinges form a mechanism. Okay, when the structure becomes unstable and eventually it collapses. Okay, and one other thing you should note it down, that in order to reach from state B, which is this one, where the stresses are in the member are at yield, okay, to the stage D. Okay, stage D is fully plastic. All the members are at fully have developed yield. Okay, so for wide flange section, so this is about 10 to 20%. Okay, once you MP in the wide flange section is about 10% to 20% of My. Okay, so once you have this type of state, okay, you come here. So based on the equilibrium, you can calculate this compressive force, you can calculate this tensile force, you can equate them. Okay, but once you solve for this equation, so you will see that for W's or symmetrical section about this axis, this compression area and this tension area is the same. So we can conclude that the plastic neutral axis divide cross section into two equal areas, which are in compression and in tension. Okay. So why we are doing this exercise? Because we know that we want to calculate that how we can estimate this thing, plastic moment. Okay, plastic moment, how we can find plastic moment. Okay, plastic moment we can find by using this formulation. So this is very clear that this comes from the material which we use in our structure. Fy is known. Okay, Fy is known. Okay, but Z is not known. So we want to find this Z, and this Z is called plastic section modulus. Okay, so we need this one in order to calculate this thing. Okay, the plastic section modulus, if you want to solve this equation, whatever at this state, when this all the members or all the fibers in your wide flange sections have reached the yield, so you can calculate the bending moment in this at any location will be equal to the plastic moment. Okay, so once you solve for that, so you do this type of formulation and calculation, so you will end up with this formulation. Okay, what is Z? This is Z. And what is A? A is the total cross-sectional area. Okay, like the total cross-sectional area of this wide flange section. Total cross-sectional area of this wide flange section A. Okay, so, and what is momentum? So momentum, you know that you can calculate that this is a rectangle, so you can divide it by 2, and this divided by 2, then you can use this, the distance between the centroids of the two half areas. Half areas mean compression and tension. Okay, the plastic section modulus you can find for wide flange section with this formulation. Okay, any question?
No, sir.
Okay.
So far, so good.
Can we take 2-3 minutes pause? So my throat is completely dried. Okay. So can we take
Okay,
two
sir.
minutes off so I can recover? Okay. Okay, thank you for bearing it with me. Okay, okay, I had some water. So we will continue with our lecture now. So the next thing is that how, okay, now before going to the next slide, you should remember that. So there is a thing called shape factor, okay? This shape factor, okay? Please remember that. This shape factor we can find by MP by MY, okay? So MP, we know that how we can find MP, okay, for a typical cross section, okay. My, if I remember that, my, I'm also human being, so my we can find, I guess, by this formulation. So this is elastic section modulus, and for rectangular cross section, this is equal to this, okay. So if you know the plastic moment or if you know the yield moment, you can find the shape factor, okay. So with this discussion, we will move on now to our next slide. Now this slide is about what we call shape factor, okay. What is a shape factor, okay. Now the shape factor gives you an idea between, or it is the ratio between the plastic moment or the yield moment of a particular cross section. For example, you can see the shape factor is 1.5 for rectangular cross section, okay. It means that the plastic moment is about 1.5 times of yield moment. Okay, for example, you just know the yield moment or you just know the plastic moment, you can calculate this yield moment if you know the shape factor. Okay, so the shape factor is an important conversion. Okay, and I just, as I have stated that this is a ratio between the plastic and the yield moment, and we have derived that how we can calculate the plastic moment. So we can come up with the plastic moment with this formulation, and the yield moment is, you can come up with this formulation. So this will cancel out. So this is Z by S. The shape factor is a ratio between the plastic section modulus and the elastic section modulus, because we know that S is elastic section modulus. Okay, S is an elastic section modulus. Okay, section modulus, and Z is the plastic section modulus. Okay, plastic section modulus. So the ratio between these two we call the shape factor. Okay, so this is just a conversion, or just give you an idea that for a particular section, what is the ratio, what is the capacity of the member. Like if a member, the shape factor is about 2, it means that the cross section is very efficient. Okay, it can develop a lot of capacity, or the bed, it can resist a lot of demand. Okay, for the sake of the rectangular cross section, so this is 1.5. So how we can go, how we derive this shear factor? So you can see there is a rectangular cross section, and the stresses are elastic. Okay, this is elastic, fully elastic. Okay, this is representing the fully elastic state, and this is representing a fully plastic state. Okay, so in the elastic, you can see the stresses are linear, and you can find it using this triangular area. Okay, now triangular area you can multiply it. Okay, so 1 by 2 into Fy, this is Fy, just sorry, so Fy into this ordinate, this is 1 by 2, this is Fy, and they have multiplied with this B. Okay, as well. Fine. So you will get this compressive force, and similarly you will get this tensile force. Okay, so the momentum you can calculate, this is about, I think, B by 2, B by 3. Okay, this is 2 D by 2 3. This is 2 D by 3, if I remember. Okay, so you can calculate that. Okay, so you just add them together and you will get this moment arm. Okay, once you have this force and you have momentum, but please remember this force and this force both are equal. So what we have done that, so we have multiplied the force with the momentum, and you will get a certain magnitude of the yield moment in the elastic state. Okay, what will be the yield capacity of this cross section? Okay, so you can come up with this formulation. Or if the member is fully plastic, okay, all the fibers of this rectangular cross sections are in the plastic state. So if you solve for this equation, so I think this B will be troubling you. Okay, so you might see this B, why there is a B here? Okay, there is no B. Okay, so why there is a B? So why there is a B here? Why there is a B term? Just okay, just give me a moment. B term, okay, in the formulation. So for the sake of discussion, so it is, you have to tell me why this B is here. Okay, why we use B here. Okay, think over it. Now, how we can find the plastic moment? The plastic moment is force times the lever arm. Lever arm in this case is D by 2. Okay, so you can just end up with this formulation, and once you take this, you have this magnitude, you have magnitude of the yield moment, you have magnitude of the plastic moment. So if we go back to our previous knowledge, or your previous like you might have seen that the bending stresses can be estimated with this formulation. Okay, mi by ix. So, and sx is, I think, the elastic section modulus. This is this by this, I by c. Okay, so my you can estimate, you can also yield moment you can estimate with this formulation. Okay, mp you can estimate, or which is known as the plastic moment, you can estimate with this formulation. Okay, so you have to take the ratio of these two in order to get the shape factor. So this is done here. So the z value or s value is over here is like, once you do go for this mp and my, you plug in these values here, so you solve for it, and so at the end you will get the 1.5. The shape factor for rectangular cross section is 1.5. In other words, you can say the plastic moment is 50% of more than the yield moment for the rectangular cross section. Okay, so this is a doubly symmetric cross section. For the wide flange section, so this shape factor is from 1.09 to 1.18. Okay, so the cross section is different, the shape factor is different. Okay, now in this slide you will see the different shape factors, okay, for different cross sections. So with this you can estimate the efficiency of these cross sections, and based on these values you can see that the most efficient is this cross section, the diamond cross section. If we use the diamond cross section, the relationship between the MP and MY will be this much, okay, 2. So the plastic moment will be, I think, to 100% more than the yield moment. So you have a lot of capacity once you use this one, if you are using this cross section. If you are using a circular cross section, so the plastic moment will be 70 times more than the yield moment. If you are using a rectangular section, if you are using a hollow circular section, and if you are using this wide flange section. So this is wide flange section. So for wide flange section, you have this much efficiency of the cross section. So these I can tell by getting the shape factors, okay? So that's why shape factors are important, okay? They are important, okay? Quickly decide about the capacity of your cross section, which it is going to develop in the bending, okay? So we are not talking about shear, okay? So this is a plot, okay? I hope the things are clearer to you. It is not very difficult, but once we do the explanation, so we get stuck in it. So every slide you might be seeing there is a lot of explanation that is coming from my side, okay? And I hope everything is clear, okay? Are you clear that what is the importance of shape factor and how can we estimate the efficiency of a cross section based on the shape factors? Okay, is it clear to you?
Yes, sir.
Okay, I think you are getting bored. I know that. Now, as I told you that what we have discussed so far is about like we can estimate we did something bending behavior of a symmetrical cross section. Okay, so how we can estimate the plastic section Z value? Okay, this Z value, plastic section modulus. Okay, plastic section modulus for an unsymmetrical shape. So this is an unsymmetrical cross section. So if you see this cross section, this is the neutral axis. So this is not a mirror image here. This is not a mirror image of this portion, okay? The compression portion is not a mirror image of tension portion. So this is an asymmetrical section, okay? But from our previous knowledge that the compression and the tension area will be the same, so you have to use, or you have to assume that this relationship holds even for the unsymmetrical shapes, okay? So how we can calculate this shape factor, plastic section modulus for unsymmetrical section? This example is about computation of the plastic section modulus, okay? Now, why plastic section modulus is important? Because we want to, if we want to calculate the plastic moment for this cross section, so we need this shape factor, plastic section modulus, okay? So how we can do it? So you can go through it, okay? I will give you some time over it, okay? So you will end up that the section modulus we can calculate with this, like summation of areas and the difference distance of their centroid from the main centroid of this cross section, okay, like this. Sorry, and so on. So in this way, you can calculate the plastic section modulus for unsymmetrical cross section. So let's go through it. So once we have to calculate the compression or A1. This is the A1 area, the compression area. So this is A1, okay? So it is equal to 15 times 1, okay? And this second area, okay, because the neutral axis depth is not at the middle of this cross section, okay? So how we are going to do it? So we will assume 15 minus this yn, okay? We have to assume the depth. And then similarly, we have to go with this one. So these two areas are equal. So once you solve for that, so you will get this yn value. Once you know the yn value, so now what you can do, you can use this formulation. Like this is A1, 8 into 1, the distance between the centroid of this cross section, this geometry to this main centroid. So you can calculate 11.5. So this is how you can proceed, and you can come up with this elastic plastic section modulus for an asymmetrical shape. So you can spend some time over it, okay? I can give you 3 to 4 minutes. So then we can start over again, okay? Is it clear to you how we can calculate the plastic modulus or plastic section modulus for an unsymmetrical shape? Can you recognize that this is an unsymmetrical shape? Tasu pade po ege jada unsymmetrical shape wale re.
Yes,
Yes,
sir.
sir.
चलो शुक्र है, पश्तो समझ आ गई. इंग्लिश तो मेरी इतनी अच्छी नहीं है, लेकिन चले. आप लोग भी कहते होंगे ये अपने साथ ही बातें करता है सर. ठीक है, हम भी इसी तरह कहते हैं, कोई बात नहीं. चलें, इसको देखें आप कैसे करेंगे. You can spend some time on this slide. This is very important, okay? So what is the time now? It is about 9:17. So you have time up to 9:20, okay? बस दरमियाना हो गया. Okay, time is up. Is it clear to all of you how you can calculate the plastic section modulus for unsymmetrical shape?
Yes, sir.
Okay, thank you. So now there is an example like how we can, now this is an example from Segway book, okay? So these lecture slides are taken, actually these lecture slides are of a professor. So we are just using his slides. So these are not our slides actually, okay? Now we have a built up section, okay? Now this is a built up section. Now the thickness of flanges and the widths are the same, okay? Now it is asking you to compute the elastic section modulus and yield moment, okay? Let me write it down. Like it is asking you to calculate elastic section modulus and at the same time yield moment. And we know that once you know the section modulus, you can calculate the yield moment with this formulation. Okay. In the second, it is asking you to calculate the plastic section modulus and the plastic moment. Okay. So these two are unknown in the B part. Okay, of this example. So we know the MP is equal to this one, and the material is given here. Okay, now the material is grade 50. For grade 50, okay, for grade 50, Fy value is 50 KSI. So Fy is there. Okay, now bending is about x-axis. Okay, about this axis you have bending. Okay, you have bending about this one. So if we go to the computation or the calculation in this example, okay, now it is saying that because of the symmetry, the elastic axis is located at the mid depth of the cross section. Okay, the elastic axis is exactly at the middle of this cross section. Okay, where this x-axis is located. Okay. The moment of inertia of cross sections can be found by using parallel theorem. Okay, parallel axis theorem. So what is parallel axis theorem? This one. Okay, like for example, if you want to compute this one, so this will be this plus area into dx square. So this is like the distance between the centroid of the geometry to the centroid of the whole cross section. Okay, so this is the parallel axis theorem. Okay, so the computation is done here. Now there are two flanges, there is one web. Okay, now you have for flanges this I bar value is same. Okay, and these are rectangular values. Okay, you can calculate using this formulation. You can calculate this I bar. Okay, so if you have done it, so once you done it, so you have area. So area you can calculate for rectangle. It's very easy to calculate. The D, it is very like it's the distance. Okay. Okay. Now once you have calculated this D value. Okay. So you are left with the web. Okay. In the web, you can also using the same formulation. You can compute this value. A and D value are 0 because D value is 0 for web. Okay. Because the main centroid of this section and the centroid of this web, they are coinciding. The dx value is 0 or the d value is 0. So that's why you will see in this table, so these values are missing. So once you calculate this value, so the I value using parallel axis theorem, please remember that there is always a confusion. You should remember that whenever you are asked to compute this thing, so this you have to calculate with the parallel axis theorem. Okay, for your cross section. Okay. If it is a rectangle, so these two values will be the same. Okay, so this C value is like the distance from here to here. This will be the C value. Okay, so you can calculate C. So this is 7 inches. So once you know the elastic section modulus, you can compute the yield moment. Okay, So the next thing is that you have to calculate the uh, what else? You have to calculate this thing, okay, and you have to calculate this thing, okay. So because the shape is symmetrical about x-axis, the axis divides both cross section into equal areas, and therefore the neutral axis or the elastic axis is actually the plastic neutral axis. The centroid of the top half area can be found by the principle of moments, okay. Taking moment about x-axis and tabulating and computation in the 4 point table 5.2. So what we do, we get this centroid value of the cross section, okay. So if we know the areas of the flanges, okay, this is the web, okay, you have to sum it up and you can put it here, okay. So once you know this y bar value, this is actually the moment arm, okay. One thing I'm wondering that over here we use this parallel axis theorem, okay. For this we have used the parallel axis theorem, and for this we are using the principle of the moments about x-axis, okay. So there is a difference between these two, okay. For elastic section modulus we have used this thing, and for plastic section modulus we are using a different approach, okay. The centroid is located, okay, with a different approach, okay. For the, please remember that, okay. This is, you can do it very easily, but just remember that this approach for the elastic and the plastic, there is a difference, okay. So once you do that, so what else is left? Once you have the y bar, you can calculate the moment arm. The moment arm is this one, and we know that what is the plastic section modulus for symmetrical section, if you remember from our previous slide. This one, yes, this is the plastic section modulus value. So once you know this A term, okay, so you can calculate this plastic modulus, okay. Plastic section modulus is, this is the Z value. So in this, it is saying the A divided by 2, okay. Now the A cross-sectional area of this member over here is 11, okay. And over here, the cross-sectional area is 60. There is a difference. So if you calculate this value, so I think this 2 is not, has been used, it is not used here. We have to check, okay. So this is the elastic section modulus. Then you can compute, once you calculate the elastic section modulus, you can calculate this plastic moment, okay. So you can go over this example, okay, think over it, like why we have used this approach, okay, why we have used this approach, principle of moments, to locate the centroid, and why we have used this approach over here. Anybody from the class, like, who can comment on it, like why we have used this approach in the computation of I value for elastic section modulus, and why we have used this approach in order to compute the plastic section modulus. Any idea why there is a difference? You have studied it.
So we have forgotten that. It was quite long ago.
So we both are at the same level. I have also forgotten it, okay. So you look into it and you let me know, okay.
Sure, sir, no problem.
Okay, you look into it and we can discuss it then, okay. So you go over this example, okay? So we can take a break now. It's about 9:30. Okay? So what time we will be back in the class?
Say 15 minutes, I guess. So
Okay, I will have a cup of tea. Okay. So you should also have a cup of tea, okay, in the break.
yes, exactly. That's what we're going to do. Enjoy.
Okay. Let me stop the recording. Keeping, yes, I'm keeping it. I'm going. How many students are present in the class? About 15 students are present. Okay.